So we discussed the solutions to the last test, and for problem 1, this is a case that's documented in the appendix, the back of the book. So this is a simply supported beam. If you look, you have the exam paper in front of you. So it's a supported beam with overhang, and come on, overhang. Where is the case? Distribute the load. Yeah, it's on the next, this one here, right? Actually, there was a moment. This one. Yeah. So, but it's or presented to you mirrored. It doesn't stop you to solve it. You just assume x going from right to left, and we have the equations. We have the equation for the deflection of the load, which may or may not be the maximum deflection, and then the upwards deflection. And these are signed. So I was expecting to see the negative and the positive with the deflections. And well, that was about it. Of course, recognizing what L and A are. Somebody took as L the full length. I don't know why. Again, the only trick was that your picture was mirrored, and that was it. You just plug in the numbers for this case G. Another thing, given the type of structural element for the problem, so it was a wide flange, 12 by 30 pound per foot. So that means it's structural steel. And structural steel has Young's modulus slightly less than regular carbon steel, at least in the way it's listed at the back of the book. So it was 26 and 10 to power 6 psi, the correct value. Okay, for number 2 problem, this is an we need to use superposition. So it's the overlap of 2 cantilever cases. One, which is this one here, cantilever beam with a load at the very end. And then you have a uniformly distributed load on a cantilever, which is Kc. So deflection at the end of the beam, and in both cases is the maximum deflection, is just going to be the sum of the two. So you evaluate deflection at B with that formula, and then you evaluate deflection at B with this other formula. Notice it's something that we discussed in class. So capital W is total load, is the equivalent, essentially the area of this uniformly distributed load. Okay, so there's this note here, and I use it elsewhere too. W, capital W is lowercase w, uniformly distributed load times the length over which it applies. So, and I've seen students using lowercase w in the formula for YB. Both are negative, so because we measure, the y-axis is positive up, and so yeah, that was it. For the third problem, I document, or here in the solution is one approach. The result does not differ. The other is to evaluate the tensile stress due to bending. So that would be here on top. So and resembles, this problem resembles the one with a T. Where is it in the book? The one with 4 forces. Let's see. I can project it. So we did a problem very similar to this one. It's the next problem, 1028, and so loads are down and offset. Here we have just one concentrated load, and being offset, what it does, it twists the solid bar 50 millimeter diameter. I changed this value in this one. So that's inducing the shear stress, and you have tensile bending on top. There's compressive below. The solution that you see here, it's by using the equivalent torque from the book. So torque as induced by P is P times V, that is 300 millimeters, and bending stress at the support is P times A, okay? And then with using the equivalent torque, you can calculate the maximum shear stress. And this is, again, this is when you apply maximum shear stress theory, and for solid round or for tubular bars or shafts, it happens that the section modulus S is half of the polar section modulus. That is, S would have been, or is, pi diameter power 3 over 32. Okay, so you calculate the maximum shear stress with this, and this is the equivalent, maximum equivalent shear stress, because we use the equivalent torque. Okay, and yeah, with it you calculate, because yield strength and shear is directly given. You calculate the design factor by just taking the ratio of the yield strength and shear over tau max. Is less than 4 for fluctuating load, and it's not acceptable. The other approach, and I believe we did this, was still on the board for the remainder of the class yesterday, and I think it's erased, the board. So we can calculate tau equivalent, tau max equivalent, and what is the formula for it? Is sigma due to bending over 2 squared plus tau squared. And again, the result would be the same. So what is sigma? Is the bending moment M over section modulus, and tau is torque over polar section modulus. Okay, so bending moment, I can lower this, we'll raise it, I can lower it. So bending moment is the one that we discussed, P times A, P times A, T is P times B, okay. And as I said, so this will be for T, this, and S is pi diameter power 3 over 32 versus ZP, which is pi diameter at power 3 over 16. All right, answer would be absolutely the same. What surprised me to see is that students that went this route, when evaluating sigma, they also included, so they took, yes, moment over section modulus, but then they added a P over pi diameter squared over 4. Why this? There's no tensile direct tension, direct compression in the bar. In this one, there isn't. Let me move this up. Okay, there's none. You could induce one if you rotate the force about the z-axis, if you rotate 90 degrees. And we can look at that problem. If you want. It's similar to the baseball, not baseball, the basketball panel curve beam. We didn't care about the curvature. And the only difference is as now you have it horizontal, and yet the force would pull rather than push towards the support. But again, I was surprised to see this on some of the solutions. So it comes down to not being confident about free body diagram. So if you're to draw a free body diagram of this assembly to figure out reactions of the support, so you remove the part from its support. This is P. We have B, and we have A. And so again, we removed it, and it's in 3D representation. So if you're, what do we have? Z towards us, Y up, and X coming out. So you notice from statics, if you have a welded joint that is a 0 degree of freedom joint, if you or in general, if you suppress a translational degree of freedom, what do you introduce? If you suppress translational degree of freedom on drawing a free body diagram, translation, that means force, okay? Because force induces rotation. So in general, I will show reaction forces and showing them in the positive direction. It will be RZ, RY, and RX. Okay? And then the support, the encastration, it's suppressing rotational degrees of freedom. So for every rotational degree of freedom, what do I introduce as a reaction? What inhibits rotation? A moment, yeah, torque. Well, torque is, what's the difference between moment and a torque? Sometimes we use them interchangeably. Anyway, so assuming also that are positive, so a positive for Z would be in this direction, moment about Z. A moment positive about Y would be in this direction, oriented this way, moment about Y. And then I have a moment about X. To make it positive, we'll have to go, negative positive. So I need to show it as like MX. And you dismiss them right away as being 0. We recognize them being 0, this reaction and this reaction. And then for moments, there's no tendency for the beam or the assembly to rotate about the y-axis clearly. And there's the what? These two, however, these are non-zero. Okay? So I drew here maybe I can do it a little bit better. So this is the torque. This one here is going to be equal to S magnitude. And in terms of actual orientation now, so it needs to oppose the tendency of the unit to rotate in the negative direction of, it's what it is. So the force tends to rotate it in this direction. That's a negative, and I have this positive. So negative and positive, they'll be okay oriented. So it's equal P times B. All right. And then as for this one, which is also non-zero, what is this equal to? And is it oriented? I mean, yeah, you can some moments and validate the orientation. If it ends up negative, you need to flip it. So what is this? This is the bending moment. This is the bending moment, and it's the encastration, and its magnitude is going to be P times A. As for its orientation now, the force wants to rotate the unit in which direction? In the direction that is negative of Z, but I have this moment oriented as positive of Z, and I same as for the early one, mx, I've got it right from the beginning. If not, you need to flip the error or put a minus, or usually changing the direction and staying with with the magnet is the way to go. Okay, so yeah, this is. But now you don't see an Rx that is non-zero from where what was earlier to where sigma was assumed m over s plus f or p over area of the solid bar, and section modulus for the same solid bar. This is not here. So let's look at the problem where it is. So I'm taking this and I'm going to, well, before doing that, let me ask you this. So I have P. And if I'm asking you to estimate how much the point of application of the force, which happens to be a hole here, how much is this hole going to the center of the hole to move down? Is this something you can tackle? We looked at this problem, have we? Trying to remember. We had something that looked like this on the board, was a load here, and was based on the text sample problem on combined stresses, if you remember. So we had this one. It's in I think we recorded this. So this case was analyzed. What's the difference between the one that we did and this one here? Notations. So B and A, nothing else. And of course, it's I have a cylindrical and then a rectangular portion. So how will that change? You have the for the rectangle, you would need to assume the, instead of area moment of inertia, well, so I for a solid is pi diameter power 4 over 64. And for this one is I for a rectangle is, if we call this H, and if we call this B, we have B, H at power 3 over 12. Before you invest into doing these analyses, let's confirm, yeah, this we got it right. As for this one, so it'll be Ix, our case, BH at power 3 over 12. Okay. So we did something like this. And then do I really need something in the background? Not really. Okay. Now, if we are assuming that I sometimes do this, and it's for my other class, which you took and you're not taking it. If this is a monkey wrench that is very stiff compared to the bar, how far will this drop? So what is it missing? Let's from the problem, this one that we did in class, it's on YouTube. Yeah, we agree that the deflection is going to be, and this is not the perspective view that I enjoy that much. This is it's called Cavalier or cabinet, where a rectangle looks like this. So versus, so if you're in CAD, the perspectives will be this one, then this one. So this is Cavalier or Cabinet, I think it's called. Anyway, so I'm drawing just the neutral axis, and this is the support. So we have, if you remember, we have two effects, or rather three effects. So there will be the rotation due to the torque by an angle theta. And then I have deflection of the original, will be rectangular in our case, portion. So yeah, it stayed straight, but now I have it bent. Okay. And then the whole, or the circular, the solid round portion is deflecting. So I have, total deflection would be y1, and then y2, and then y3. So y total, again, for the problem based on the one in the textbook, although that was for combined stresses, but we did some deflection analysis. So it'll be y1 plus y2 plus y3. And I said that y2 is going to be theta in radians times the distance. Again, this is A and this is B, so times B. Do you remember? You may want to go back to the YouTube. You can watch it in faster than the normal recording speed. But yeah, we looked at this one. This is 90 degrees. Now I'm asking you, if this is a monkey wrench that is very stiff and you ignore that its deflection compared with that of the bar, which term will be neglected of the three? Again, this is theta times B. Which one will be neglected? Y3, because it's very stiff rectangular portion is going to or will be minimum bending, minimum deflection, and this goes to 0 for a stiff wrench. So assuming this is a wrench. And I do have problems. Probably not going to retake, we call it now design machine elements. Anyway, so yeah, this was it. Let's look at, I'm going to raise this. Let's look at the same problem, but where the force is oriented. So I changed, I erased it and then came back. So let's assume now that the force is, it's oriented at some angle. And if we just say it's horizontal parallel to the x-axis, so I call this px and I call this py, which together make for a, I'm not showing both the components, and the original. The book that I used to teach statics years ago, it said, and dynamics, it said don't show both or distinguish between the x and y components, or when you resolve an original force. So if we call this P original, again, the problem that you had in that yesterday test was just this load applied. Now if I'm adding this one, we'll make for a resultant that it's at some angle. Okay? And we can assume P is 1,000, like it was newtons, and we can assume some angle. So we can take this at 30 degrees. case in which Px and Py can be calculated, we can do that. Let me see, do I have the calculator? Yes, I do. So this is going to be 1,000 times 30 sine, and 30 sine is 0.5, so this is 500 newtons. And then this other one would be 30 cosine times 1,000, and this is 866 newtons. Okay, so is it clear what I did to the earlier problem? Do you follow? Okay. Going to erase this. So let's see what we are dealing with. How does this change? Do I need these? Possibly. I take this because now it's the case. We don't look at deflections. So I erase this too. And I'm going to erase this also. We'll rewrite it at some point. Or reuse the results from before from the solutions that are on Blackboard. Okay. Okay, so on the free body diagram, what is no longer valid like it was with this one here? This is no longer 0 because of this force. Okay, and there are other changes too. This also is no longer going to be 0. So how big, what's the magnitude of Rx? Now, if you look at the problem. Just px. We're summing forces in the x direction. Again, you could do it. You can write it. Sum of force in the x direction. You can take it, small steps. But otherwise, this is going to be 500 newtons. And I reversed it to where, they're counteracting. Their sum is 0. This is positive over x. This is negative over x. Same magnitude, go to 0. This one here, Ry, I never wrote on the figure. So what is Ry equal to? $866. It's the orientation correct? It is, because this is down, this goes up. So I don't need to flip. I'm sorry? Well, it was, but I changed so you either change the sign or you reorient the vector. I have a preference to reorient the vector and just put the magnitude on. But from calculation end up with a reaction that is negative, it means that the assumed orientation of that reaction force was not, you didn't get it right. Not it was wrong. Okay, so let's look at the moments now. So we have, because of this force and because of this force, we have a torsion, and it's going to be B. Yeah, I can, this was 300 millimeters. And this is 450, or was in the problem. Yeah, 450. So the torque or the twist of the bar is going to be by this torque that is what was P before, now 1,000, now it's 866 times, so 866 times B. And we can calculate. And then I said we have a moment that is no longer 0. Here too, instead of P times A, I'm saying 866. Could have said P times cosine of 30 degrees. Okay, and it's not 0. And this one was 0 before, but not anymore now because of the horizontal force. How big is this moment? And what kind of effect does it have upon the beam? Well, this moment is going to be equal to px times b. So I could have instead of a60. Okay, px is 500 px, that is times b. And in terms of its orientation, if you look at the part, due to this horizontal force, it has the tendency to rotate the right-hand screw. If you turn it, it goes down. So, and this is up. So yeah, we've got it right, or we don't need to flip the vector. This is py, and this is py. Okay. So I do have two bending moments. This is a bending moment, and this is a bending moment on top of a torsion. And then because of this axial load, or yeah, the axial force over we're discussing the cylindrical portion of the Riemann, bending moments will be maximum here because you have, like where? Times A, and this is times B. Yeah, so because of A, I mean, if you take it elsewhere, this value, it's less, so it's maximum bending moment. This one is maximum here. It's not affected for this bending. So this bending does not change. So it's pure bending in the horizontal plane. And then on top, like I said, I have the axial load. So if I'm to calculate the stress on the same location, I have the longitudinal stress sigma x, and then I have the shear, so pound, not on this, but the other surface, and tendency to rotate. So this is going to be tau. It's crossing x in the direction of the xz, and this is sigma x. So sigma x is going to be the two components now. So because of Rx, so it's going to be primarily bending. So it's going to be the same, or py times a, that's the moment, over s of the solid round. And because tension is on top, compression below, to that tension on top, I'm adding the force, and it's px over area of the solid bar. Tau xy or tau xz, it's same as before was the amendment that I'm using py instead. So it's going to be py times b, that's the torque, over Paul section modulus for the solid. Okay. However, this is not, if you take these two together, you don't get the maximum. So is it clear? It was more of an exercise of resolving forces and statics than, and it's what I'm seeing some deficiencies on the preparedness of some of the students for this class and other classes that I teach. But again, this is not going to be the maximum stress. The maximum stress occurs somewhere in between because both combine generate the maximum bending. So if you're to work on, you load it at some angle, or you pull in a colleague forces down, it's going to yield on a direction that is neither horizontal nor down. It will be in between. And you can get, I'm anticipating this is for structural classes, for my class. So there will be a resultant moment, which is easy to, you just sum the moments as orthogonal vectors, right? If you have two orthogonal vectors, how you get their magnitude? So it'll be, first of all, which are the vectors? It's mz and my. So it'll be my square plus mz square. You've seen this before. You have two orthogonal values, Pythagoras theorem. This will be the maximum moment that will go in evaluating sigma. So this vanishes, you'll have this instead, and everything else the same. The tensile stress, you take it over the cross section due to axial load. It's the same, and it's the same everywhere. The bending stress is maximum here at the support. And then shear stress caused by twisting, it's tangential to the outer skin of the bar, and you observe the one that is, I said that will be somewhere in between. So as you apply this and this forces together, one will tend to bend the part this way, the other one down. So maximum tensile stress will be somewhere, behind at some angle, not on top, not horizontal, at some angle. Okay, we can even calculate that angle from this same formula. So you have two moments. What's the angle between the two? Okay, so this is tau, the one that torque over polar section modulus. And again, you take it with the orientation that or over the portion of the outer skin that you combine it with the maximum bending. Okay. So yeah, this is where you would see a term like force over area, and that's even as uniformly distributed. The book has it drawn in several places. So for a round bar, the bending stress, it's equal tensile amount of tension. It's equal to amount of compression, and then you add the direct tension due to an axial load, and it gets you more tension and less compression. I drew this at least twice before. Okay, so what was this piece? F over A or P? Well, in general, F over A, because otherwise I'll need to look at PX. So F over A area is going to be, my drawing is not at scale, so could take this and place it here, make this longer. So this piece plus this one will make for this length. And then I take this, subtract from here, I'm left with this. Okay. So yeah, this is M over S positive. This is negative M over S. Here I have negative M over S plus F over A. Here's M over S positive plus F over A. Okay? And that was the case of the problems that we solved was the baseball, no, I keep on saying baseball, basketball board and goal basket that you remember with a down force, a player that's hanging. Actually, they do hang on the side end. And we even contemplate or looked at how we can determine how far this is going to drop. It wasn't a complicated problem. Do you have questions that you want to ask? Otherwise, I can do another problem that is a bit more involved. So expect, as you can see, that it builds upon, well, firstly, static, the prerequisite, but bending, shear force bending moment analysis, and it can be extended with deflection. So there's one. So yeah, if you can just say, I want you to solve certain problem from the book, we can do that. Otherwise, 1092. Is that a Mohr circle?
Yeah, no issue. So 1092, and we can verify with the spreadsheet that is. If you try on your own the spreadsheet.
Yeah, it's just forming the circle that
Okay, but as you do problems on your own, more circle you draw them by hand, and then you can go to the spread. And there are online apps that do more circles. But I think they don't always match the sign convention in the book, based on my knowledge. But I know there are apps, and they are, with nice graphics. Or at the minimum, you may find more of those. They just calculate the principal stresses, and so it's equations only without the drawing of the Mohr circle. Yeah, we'll do it in just a little. So there, we're having two compressive stresses on the element and a shear stress that is counterclockwise. So problem is 1092, and I think I can blank screen. So 1092, and the stress element, the original stress element, which we know had we like to orient it, was the part in a convenient way. Usually x is the long axis of the element. So we have sigma x. I don't put negative because I represent the stress towards the surface, 840. And these are kilopascals. And likewise, the sigma x, 840 kilopascals. And then in the y direction, we have also compressive stress. So this is sigma y, and it's 335 kilopascals. And this one too, sigma y, 335 kilopascals. In addition, we have shear stress, tau xy, which is counterclockwise. So it means is this a tau intersects the x-axis, points the direction of y, so xy. And this is 120 kilopascals, 120 kilopascals. And now I can complete the circle, or the element with the other stresses. So tail to tail, head to head. Okay, so this would be, there's a bit of crowdiness here. So tau, this would be tau yx. And likewise, this one, and this is tau xy. Their orientation is based on the direction in which they rotate or tend to rotate the element. And then we have sigma z, which is 0. That's the ambient pressure. It might not be 0 as a rule. We can have this whole thing, being subject to hydrostatic pressure. Okay, so we're going to draw the Mohr circle. I need to make room for the stress elements. More stress elements. I can draw a stress element, and yeah, I can draw the Mohr circle here. So I'm looking at the values. So they are negative values. So the circle will happen mostly to the right. And so we draw the tau axis. And this is sigma, this is tau, and this is clockwise. The up is assumed clockwise. The figure from the book that we follow is on page 610. It's figure 1030. So we know that the center of the circle is at sigma average. Sigma average,
there'll be sigma x plus sigma y divided by 2 with their sign. So even if they show on the board as positive or not the minus, we take them as minus because of the way arrows are oriented. So 840, I said plus 335 divided by 2. That's 587.5, but I put a minus. So 587.5 kilopascals. And then I need the radius of the circle, and that's going to be sigma average minus sigma x. It's 1 over 2 sigma a minus sigma y. So 1 over 2. Well, let's take the shorter steps. So we have a and b. A is 1 over 2 sigma x minus sigma y. And b is tau xy. Their sign are not important because they get squared to get the radius. So tau xy, that was 120. And this one here would be, well, I put a negative, but again, the sign does not matter in this analysis, in this case. So 840 minus 335 equals over 2 equals, that's 252.5 negative. And kilopascals. Okay, so with this result, I can get the radius is going to be 252.5 squared plus 120 squared. So I get this as squared plus 120 squared equals, and take the square root. And this is 279.6. 279.6 kilopascals. All right. So I can start drawing the circle. So I need to place the average, and then to the average I'm adding the radius. So what will that in further moving to get it to the far left? So this would be plus 588, just roughly. So I have 800 and maybe going exceeding or approaching 900, maybe going over 900. So 100, 200, 300, 4, 5, 6, 7, 8, 9, negative 100, negative 200, 300, 800, negative 900, negative. And I more or less, so I started shrinking, and this is 1, 2, 3, 4, 5. We'll probably go above. I mean, just having radius is not that big, but at least for the 2D circle. So 100, 200, 300, 400, 500. And then going below 1, 2, what is this? 200, 300, 400, 500, 500, 600. So negative 100, 200, 300, 400, 500. Okay, so we're going to place on the graph the center, negative 587, negative 550, 575, 7, it might be like here. So this is the center of the circle. Point O of coordinates 587, negative 0.5. And I'm showing the two points on the diameter points. So one is negative 840, 850, 840 with tau xy, and it's clockwise up, so I need to move down 120. It will be like this point. So this is 1.1 on the circle. This is negative 120. And I'm getting the other point on the circle, which is 335 in tau ix. So 335 and tau ix is having the same magnitude, but it's positive. So if you look at tau ix, this is a clockwise shear stress. It will be above. So this is 0.2 on the circle. And then I draw the diameter through the connecting points 1 and 2. And the x-axis of the element, the stress element on the circle, is going to be the one that connects the center with 0.1. Is it clear so far? Okay, so I can now draw the circle. I said I'm going to use red color. It's helpful to add the mirror points to help get a better circle. All right, so it goes like this and like this. And then, again, with drawing tools, it's much easier. All right, so I'll have sigma 1 here. Actually, no, I'll have sigma 1, 0 here. Will be the case of a 3D circle. When I said that the circle, the 2D circle, is all the way to the left or to the right, I need to consider the 0 stress, which is sigma z. And that's helpful to evaluate the true maximum shear stress. So this will be sigma 2, and this is sigma 3, which is the smallest with their sign of the 3 stresses. So what is sigma 2 equal to? It's going to be the center of the circle plus, that is sigma average, plus the radius. So negative 5, or I could say 279.6, negative 587.5 equals, that's 307.9, 308 with a negative sign, negative 308. And units are kilopascals. Sigma 3 is going to be the center of the circle minus the radius. So negative 5, or I could say 587.5 plus 279.6 equals, and I take it with negative number. So negative 867. Negative 867. It didn't go all the way to 900. Okay, but this is only the 2D circle. To get the full 3D circle, I need to draw a circle that goes through the limit that is sigma 1 and the sigma 3. So that will be this one. Oh, it's a little bit humped. And this is the one that's going to give us tau max. So tau max, the true tau max, the one that you would, using maximum shear stress theory, you would compare with the yield strength and shear of the material. So what is tau max from the figure? Well, you take this and divide by 2. So it will be like a sigma 1 minus sigma 3 divided by 2. So and this is 0, so it's 867. And it's 433.5. 433.5. Yeah, I almost got it. If I adjust it a little bit. Okay. So yeah, we've got tau max, the true tau max. if this, so we were not told. So it looks like it was clear. You're able to follow. What was where did you get stuck? What was unclear when you tried on your own?
Oh, it was just the circles. Like the first idea was fine. This one, when you said that
The 3D
one
circle?
was zero, I didn't understand why. What I see is because it's on the negative side. So,
Well, we have it's not a rule. It can be other than zero. You can induce a tensile stress maybe, but the easiest to is just imagine this being either to the inside of a pipe, although how do you reconcile the compressive stresses? So yeah, if this is instead of being zero normal stress, it's say 100, negative 100 kilopascals, sigma 1 will shift here. So if I have this submersed in a compressed fluid, you say a hydraulic system, and I have 100 kilopascals of ambient pressure that's acting, compressing the surface, then sigma 1 is going to shift to this point. The 3D circuit becomes smaller, tau max becomes less. Okay. A tensile stress, how can you do a tensile stress? Maybe, by pulling. Again, these are numbers that were given to us. The more involved always, in my opinion, is to figure out these actual stresses before you draw the circle and calculate tau max or sigma 1, sigma 2, and sigma 3. Okay, so now I have sigma 1, sigma 2, and sigma 3. I can draw the stress element or the principal element. So the principal element is going to be rotated. I'm looking here at so it's going to be rotated half of this angle in a clockwise direction. So this is 2 phi. And by just guessing from, so I need to take this element. If you can imagine, on the circle is, all flipped and with x-axis going this way. But I'm back on the element, and I need to rotate half of this angle, and I'm trying to guess it. And I have it's probably the full angle, not half of it. I'm drawing the same rectangular or square element, and I'm going to show 2 compressive stresses. One would be, so as you rotate it, this surface is this surface, and it's going to experience sigma 3. And so that's the large compressive stress. And it's just the axis. So this will be sigma 3. And then we have the other stress, it's sigma 2, and also compressive. It will be less. So sigma 2, and sigma 1 is 0 on the surface. So we get negative 308 or 308. The orientation of the arrow tells us that's compressive, and this other one 867. Both compressive. All right. So this is the principal element. Does not have shear stresses. So that's the definition of the. We're part of the definition of the principal element, that there's no shear, and these are maximum or minimum. Okay, and then to draw the maximum shear stress element, you have to take this and rotate it further 45 or backwards 45. So how'll that be? I have to maybe move here. Okay, so, and on the circle, it will be a matter of going, so I have the x-axis to encounter the tau max, this tau max, not the true tau max, the tau max on the 2D circle. I need to go counterclockwise, which I did. So the x-axis now, so this was the x-axis, and I rotate the x-axis prime would be this way. And then going the other way, x-axis second would be this way. The angle between them being 45, between this element here and this element here, was the orientation. Keep on orienting. If I'm to measure from here to here, I'll have to take this angle, and will be 90 degrees minus 2 phi, the true angle, but the one here really would be, so this is x, this won't be 90 minus 2 phi divided by 2, or 45 degrees minus phi. So what is phi? How do we get phi from here? So it's an arctangent. It's will be half an arctangent, 1/2 arctangent of, will be really b over a that we already have. And I take them as absolute values because I have the drawing that's helped me. If you just use formulae, sine is important because it tells you that is an angle that is measured. You know, in trigonometry, in geometry, a positive angle would be counterclockwise. So angles are positive counterclockwise. So the arctangent, we said, of b over a, and it's 1/2 arctangent of 120, and I take absolute value over 252.5. 120 over 252.5 equals arctangent, and then divide by 2, this is 12.71. Meaning that this angle here is going to be, I subtract 45, it's 32.3. Or rather 32.3 degrees. Are we better now? If you want to take a photograph of the, or it'll be on YouTube, take your own photograph. Let me know if you have questions. I'll go back to a problem from early chapters, reflection of beams, that is a bit more involved when it comes to figuring out reactions of the support. Unless you have your own preference, what problem to do on the board. Otherwise, we'll do, we haven't done 844. Or was it the homo, or it's on the list, but wasn't a test problem. It wasn't something we did on board. Student-driven class. Student-driven class. Do you have a question, a problem that we want to solve, or I can do the 844? Let's do 844. So what does it say? An aluminum association standard channel is to be specified to carry the load shown, to produce a design factor of 4 in bending. The legs of the channels are pointing down. The channel is made of 6061 T6 aluminum. For the channel selected, compute the maximum shearing stress. We know that bending stress is, so I'm lowering this, I don't like the overhang. So the bending stress are always the more severe stresses, unless you work on like locally and you have step shafts. But this one is a constant section, so we use bending as a
stress as a predominant load, select the channel, and then evaluate the shear stress. Okay.
And
one other thing that I should look in camera now. So one other thing that I noticed that students don't know did not interpret the vector force was a little horizontal line, like across at the tail as support.
a reaction to support. So here we know that they are support.
It's a simply supported beam.
And this will be our RA at some point. We label this as A. And then I have 4 inches.
And then there is there's symmetry of geometric symmetry, but no load symmetry. So we have
2,500 pound force.
and then we have
Another support 4 inches from the end. There's an overhang. And so this is 4 inches. And in between I have 10 inches. And then at this end, I have a down force that is 800 pounds. And the channel is chosen
was the flanges down. Okay.
So we need to, and I overdrew these arrows here. We need to figure out the reaction of the supports. Let's label some points. I have A, there's B, F, C, and D. And to get RA and RC, we need to sum moments for RC about A, for RA about C. So sum of moments about A, we have equilibrium. We seem positive to be counterclockwise for this analysis. So what do we write? Can you help me?
2,500 or negative 2,500.
So we have indeed assuming counterclockwise positive moment. So we have a negative 2,500 times 4. And then what's next? I have RC, yes, and that's a positive moment caused by RC times, what's the arm of the moment of the force?
Inches.
Yeah, 4 plus 10, 14. And then I have another negative moment due to the 800 pound force. So 800, and the arm of the force is going to be 18 inches. Equals 0. So I can solve for RC now. So RC is going to be to the right. So it's going to be 24 times 4 plus is 18 over 14. And
2400 times 4 plus 800 times 18 over 14 equals. So it's 1714.3. 1714 pounds. I'm sorry?
Wouldn't it be 2,500 times 4?
I missed something. 800 times 18 divided by 14. Oh. Yeah, this is I joked about this before. Mutation that can develop into positive traits. 2500 times 4 plus 800 times 18 equals over 14 equals. So 1742.9, 1743 pounds easily. Okay, and now we sum moments about C, and that will give us RA. So we have negative RA times the full length of the beam, rather 14 inches. And then I have a positive moment due to the 2,500 pound force, and the arm is 10. And then I have, so negative, positive, and this one is also negative, the 800 pound force cause a positive, rather negative. So it's times 4 equals 0. So I have RA is, keep these, move RA to the right. So it will be 2,500 times 10 minus 800 times 4 over 14.
And 2,500 minus 800 times 4 equals over 14 equals.
It's 1,500 and 57.14. I ignore those because I rounded here. So yeah, we can verify force in y direction whether they are 0. Both RC and RA ended up positive, so it means that the way these are assumed, it's correct. We don't need to flip any of the reactions. With this being larger and this smaller, I mean, you can increase this up to a point that you start lifting this in from the support, case in which you need to, the support needs to be holding it, like this RA will end up being down force. So yeah, I'm going to write the magnitudes on the drawing. RA 1,557 pounds. The other one 1,743 pounds. Okay, so yeah, I could write it. So 1,557 negative 2,500 plus 1,743 minus 800. Is this near 0 or 0?
1,557 minus 2,500 plus 1,743. 743 minus 800
is 0. Exactly 0 because I discarded the 0.1 whatever in this rounded to full integers. So now I can draw the shear diagram. And we begin, or let me also look for a moment diagram. Let me move this a little bit further up. So I have 1,557, and then it stays unchanged, and then there's a drop by 2,500.
So 1,557 minus 2,500. This is negative 943.
So this is negative 943. And this stays unchanged, and then I have a jump up. It is, well, drop is down, jump is up by 1,743.
So plus 1,743 equals,
that's 800 as expected, because the diagram will close to 0 once I pass point D. So a fraction of an inch left or right of D, I get to 0. So this is 800, a positive. Okay. With this whole thing being 2,500, this whole thing being 1,743. This was V and was in pounds. Then I have the moment diagram, and you're expecting two cusps. So the moment diagram starts with the maximum slope This would be the maximum slope. I look at the value. So these are slopes. Actually, no, this is the max. No, I'm sorry. This one is the maximum slope. So, and it's positive. So a moment diagram moves up, and then this is where a maximum happens. So what is the magnitude right before point B? This is going to be the area 4 inches times 1,557. 1,557 times 4. That's 6,228. 6,228. Okay. And then the slope changes to negative but lesser slope. So let's see, you'd expect the moment diagram to go below the x-axis. So we can tell the magnitude of M at point C by just subtracting or adding this negative area. So I have 6,228 on a calculator and subtract 943 times 10. That's negative 3,202. So this one here so this is negative 3,202. Again, we're working on moments, and moments will be in pound inch. Okay, so this is positive. We went negative. This should close to 0. I still have this. So if I'm adding 800 times 4, so plus 800 times 4, I need to get the it's negative 2 because of round up or rounding. Okay. So yeah, diagram close to 0. And we have the peak moments. How do we get where the moment goes to 0? That's where the slope, if you remember, we have, so V is, in general, dW of x over dx. X is the axis of the beam. And then we have M is dV of x over dx. And then I have, how's it go? Theta is 1 over EI times d M over dx. Am I saying the right thing? No, it is not. So M is dV over dx. Theta is, and then no, theta is dy over dx. And I got stuck. So what are the equations? I don't know where I mean, it's not part of the problem, but just a review. And I said that successive integration is not going to be part of the exam. So I need to make sure I'm writing the right equations on the board. So moment area method. This is for deflection, and yeah, I'm summarizing the deflection equations, or beam equations are also known as. Okay. So yeah, M over EI. Come on, book. Somewhere here. All right. So yeah, this is fine. This is fine. This is also okay. And then I have y equals theta times for each segment. Well, there are a number of equations. Since I started, let me just put one that's valid. So M
equals EI d2y over dx squared, and I can write EI times d theta over dx because of the above equation. All right. And this is, yeah, d theta over dx. But if we're to find A and B that locate the maximum bending moment, which will go to 0 when the slope is 0, in virtue of this equation. So how do you go about that? We had to do it on occasions. So successive, or rather symmetry, sorry. Symmetry, similar triangle is a way to go. So I have A plus B is 10 inches, and then I have A over B is 6228 over 3202. Okay, so I can further say that that is 10. So from here I get A is 10 minus B. So there will be 10 minus B over B is 6228 over 3202, which is 10 over B minus 1 equals, and or I could just say equals 1 plus 6228 over 3202. Okay, so I can solve for B from this last equation. 6228 over 3202 equals plus 1 equals, I have this business, and I take the inverse 1 over x and times 10, and it gets me B. So B is 3.3955, we can say easily 3.4 inches. And this other one is the difference, will be 6.6 inches. I said inches. Okay. Anyway, so we have the, well, we can tell the maximum moment. It's this one here. This is M max. And if we have M max, we can move forward and figure out the section modulus for the channel. Maybe we, at this point, maybe we should go and look at the channel. They are presented in the appendix in the vertical orientation. So this is YY, and this is XX. Working with section modulus, it's where it's convenient because you have one single value to match with what's available, or select from the table. So we know that the material for this channel is 6061 T6. And you go back to the problem. So problem is 8844. Okay, so we have 6061 T6. 6061 T6 aluminum, for which yield strength is, and it even says, well, it says where the sections are. So we need to go to the back of the book where properties of materials are listed. They are after section. So structural steel, typical properties of aluminum. So our 6061 T6, page is 787, and yield strength. Okay, it says design factor of 4 in bending. Does not say that for repeated loading. So we go with yield strength and N equals 4. On page 790, a design factor of 4 is associated with repeated loading, and for bending stresses, actually no, it's 8. Repeated loading for bending stresses, its design factor is 8. So an overly conservative static loading, we may say. All right, so N is 4. Yield strength in shear for this 6061 T6 is 276 megapascals. 200. Oh, I'm looking at the problem working in PSI. Okay, yeah, no problem. So we need the KSI value. That's 40 KSI.
40 KSI. Okay. Anything else? No, this is what we need from here. So, and then I said, yeah, if we go to where the channels are, aluminum sections. So American Standard, EU steel, and then US units, aluminum, smaller sizes. So I'm on page 765, and you can see the channel represented with the web vertical. So yeah, we'll be looking at an rather SX value that is at least the one that we calculated. Okay, so channel in the appendix is represented this way, with this being X and this being Y. Ours is rotated, so again, of interest will be an SY. We need to find it. And we state the design equations. Design stress is going to be maximum bending moment over SY minimum required equals yield strength in shear divided by design factor, and that's imposed N equals 4 design factor. Okay, so what is this equation equal to? Have the maximum moment 606,228. This is the unknown SY. I should say SYY, because we SYY minimum required, not to in capital Y. Not to confuse it with this other one. With this one here. Equals 40 KSI. We need to work in PSI, so I'm adding 3 zeros over design factor of 4. So from here I get SYY minimum required of 4 times 6228 over 40,000. So let's see what this end up being. 4 times 6228 over 40 exponent 3 equals. This is 0.6228 inches at power 4. Of course, we will not be able to find a value that is exactly this, but we need something that's at least that much inches at power 4. So back to the appendix 6. And so let's see what's available on the SY column. I need to go to the next page. US units, aluminum, European. Oh, is it documented? Do we have anything? SY, I said. It's a bit big. We don't have anything. A6B, oh, the solution.
No problem.
Oh, the appendix A6B. Yeah, these are small sizes. Okay, 6B. So let's look at, yeah, I said SY. And there's one that's 0.64. That's entry G, which is a good candidate, and then the one on top, entry F. So we can specify C5 by 2.212. So specify was C5 by 2.212. Okay, so we've got this one, and problem is not over. We need to calculate the, does it say the true bending stress? The maximum shearing stress. Okay, so the maximum shearing stress, that's, let me bookmark it. So let's see what we have available information. That's, we have the T sections. So I'm going backwards in the chapter, and this must be an approximate formula. Okay. Well, C channel is not documented, but we have I beams. Okay. So in terms of behavior to shear, whether you have it this way or this way, does not make any difference. Is that correct? It's just a matter of moving the core, the web. So, general shear formula. And so thin web shapes. So we have maximum over area of the web. Now there's get it. I have a C channel. It's not like so. So it's C. It's oriented this way. So the way out is to calculate actual first moment of area. So we need to calculate first moment of area. I have the centroid, and there is information in the table. Yeah, I haven't contemplated the problem all the way to the end, but we can take care of it. So there's no approximate formula given. We use the general shear formula. Tau is going to be V over first moment of area over thickness over I area moment of inertia. Okay, so we have V, will be the maximum V from the diagram. That's clear. It's this one. So this is V max. Okay. And then we have the area moment of inertia. This is going to be the our IYY that goes with this S. And then the first moment of area. So thickness, it's going to be really this one and this one. And then first moment of area, it's going to be maxed. Is it going to happen exactly the centroid? How's this problem solved? Maximum shear stress. I wish I've looked at it all.
Can we just do it over the area?
I'm sorry?
Well, in terms of shearing behavior, so this is, I started saying that if it's a channel like vertical, it's equivalent with an I-beam. If I take this, it's going to be, I just move the flanges to the middle, and it's the same thing. It's just a matter of how you distribute the loads. Of course, a channel oriented this way versus an I-beam, the only difference is that when you place the loads, they need to be through the flexure center. And it's a section that we covered.
One equation for the rectangular, which is
We have the equations for the rectangle. Yes, we have there are T sections documented. Okay, so it looks like, so I'm on page 474, and there's some graphs here. So it shows the neutral axis is the maximum shear stress. Now we can leave it as is. We can treat it as a T section. So it means but expectation is the same, that first moment of area to be evaluated, like what is above or below the centroidal axis, which would be y-axis here. Okay, so yeah, we need to use the general formula. This will come out from the table. T is going to be twice the thickness of the flanges. This is the web. And now Q, we can take either the above or below. That might be a good opportunity to verify what I kept on saying, that you either take the above or the below Q. So yeah, let's look at that tau there. So let's put some value, tau max. So V to begin with, it's what was it, the maximum? 1,500, 1,557. And then I have Q to calculate. And then below, I divide by I y from the appendix 6, 6b. Properties channels. Yes, so that was IY was 0.98. Yeah, I was there. I'm seeing annotation 0.98 inches, so 0.98 inches at power 4. And then for thickness, from the same appendix, I get the typical, it says, so web thickness, actually flange thickness. So flange thickness is 0.26 inches. Okay, so 0.26, 0.26, but taken twice. Okay, so all we left is to evaluate Q. First moment of area. And first moment of area, remember, is the area of the portion of the section above or below the line that we are evaluating it. And again, we expect tau max to occur on the centroid. So this is the centroid. And this is the where tau max occurs. Okay, so we need to go back to the same appendix to evaluate here. So we have rectangles. There's going to be, depending on how we divide it. So I'm redoing this figure. So we have, again, the area. This is the above area, AP. And I have the centroid, and I have this was the web thickness. The smaller value is 0.15. I think it was 0.15. Yes, 0.15. 15 inches. This is the 0.26. Okay. And then I have this distance from the that positions the centroids, the lowercase x value, and that's 0.73, 0.73. So I have this distance now
0.73 inches. Okay, so let's see what is the area, and then we need to calculate where the centroid is. So we have like how many parts? 3 parts. It's probably easier to just go with what's left below. But I said it's a good opportunity to verify the approach, whether we take the below or the above. Okay, so firstly, what's the area? AP times the distance between the centroid of the assembly and the centroid.